Hi everyone, welcome to the AstroLaunch podcast. I'm your host Amy, and today I'm so excited to invite to the podcast a space scientist and astrophysicist who works at UCLA and with NASA studying space weather. Today we'll talk about their journey, their research, and what it's like working in space science. Hi Souvik, welcome to the podcast. It's so good to have you here.
Thank you. Thank you, Amy. Thank you for having me. Thank you so much.
So to start off, can you tell us a little bit about yourself and your job?
So I am Souvik Roy. I did my PhD back in India. Currently, I am a postdoctoral scholar at UCLA, and also I work also with the NASA Drive Center for Geospace Storms. And yep, that's me.
Okay. And what first inspired you to pursue a career in astrophysics and space science?
Okay, so the story goes back to when I was a toddler. Um, I come from a village in India where the night sky was actually the night sky, less light pollution and all. And that time, I mean, it gave me a curiosity about the life other than us. Much later, when I did my undergraduation, we call BSc in India, I started learning physics and how physics can describe our world. And then in my graduation, which is master's in India, I took astrophysics as a specialization because all those curiosities I built up as a toddler, I thought that I'd get answers. I got answers for most of it, and then I thought, let's do PhD to find some more answers to my question. And then I completed my PhD in space science. Yep.
That's
And
so
now
like,
I'm here.
no, that's so similar to my story too, because like when I was in India as like a child, like I agree the sky was like so much clearer and there was so less
Yes.
pollution. And
Yes.
my like thinking of aerospace and wanting to learn about space also started when I was a toddler, so I can totally relate to why you wanted to do this.
Yep. That's basically very common if you have a clear sky to
Yes,
see in your toddler life.
yeah. So, can you tell us a little bit about your journey from studying physics to becoming like a researcher at UCLA?
As I told you, it's I took physics honors. So my graduation was on physics. Then I specialized on astrophysics. Then I joined Indian Institute of Science Education and Research, Kolkata, which is in short IISc or Kolkata in India, for my PhD. I did my PhD on modeling space weather environment. So it's a part of it is computation physics, a part of it is space weather or solar terrestrial physics. It's a combination of computation and physics. And then after that, I got an opportunity to work with the NASA Drive Center for Geospace Storms at UCLA. So then I came here at UCLA, and now I am working with more complicated models, way more huge data set, and basically the same goal that I started in my PhD life, but on a much bigger landscape.
Oh, and what are some challenges that you faced along the way?
Okay, so the answer in short is uncertainty. So research overall in any subject line has you have to understand it's open end. It's not always converging to somewhere. It may diverge from what you think. So handling uncertainty is one of the key challenges when you are doing research. For me, it's also the same. And other than that, I would say that how should I describe it in uh, let's say um, failure is a part of life. So we don't know everything always. learning and keep learning is a challenge, and that's all. Like you have to keep learning, and you know that there will be uncertainties, so you have to know how to dodge uncertainties and how to like succeed with the uncertainties and keeping learning, keep the learning switch on. Yep.
Yeah, that makes sense. So now we're going to talk about like your research itself. So for the people in the audience that don't know, what is space weather?
That's a good question. I answer this a lot to people. So space weather is basically weather, but not for this lower latitude, lower altitude. It's much higher. Let's say it starts from 100 kilometer from the Earth's surface and goes as long as you can think about in the space. So for Earth is a magnetized planet, and our star Sun is also a magnetized body. And Sun tries to create a space environment for the Earth because the magnetic field of Sun, the magnetic activity of the Sun varies with time. So it's like a weather for the environment of the surrounding of the Earth. But instead of clouds and rains and storms, you have like plasmas, magnetic fields. Storms are also there. So you have a quiet time, you have a storm time. So that's all space weather is.
That makes sense. And how can space weather affect Earth and our daily lives?
Oh, that's a good question. So um, let me give you a anecdote, a small story. I would love to say this in this way. So let's say you are on Santa Monica Beach, okay, and then it's a breezy, calm day. There are cool breezes coming out. People are enjoying an evening, or let's say the sunset. That's like very common. That's like almost everyday scenario. And then you suddenly saw that there will be a storm coming. And you shouldn't be in the sea beach, or you shouldn't go for surfing. The similar way is for the space weather as well. We What we mostly see is called quiet time, and that's like almost omnipresent. That's 24/7. We have solar wind coming to Earth with a massive speed. It's nearly about 300 to 400 kilometer per second. But that's very normal. That's like the normal evening breeze on Santa Monica, if I just compare in that sense. But then there are storms that are also coming towards Earth, and that's where it's become challenging for scientists like us to understand and predict such scenarios so that we can avoid problems. And the problems would be on daily life. I mean, we don't realize how space weather can like affect our daily lives in the deeper sense. But everything that includes a technology based on space and satellite are susceptible to an space weather storm. Your GPS, your satellite navigation systems, your flights, aviations, um, maybe mm, in earlier days, even in modern days, also your electric lines, the grid transmission lines. You have oil pipes or gas pipes, large gas pipes, intercontinental pipes. All of these are susceptible to adverse space weather, and we have seen even recent news where we lost satellites because of an event and all this. So yeah, more than we realize, space weather has an impact on our daily life because of the technological infrastructure we have on outer space. Yep.
That makes sense. And how do scientists predict like the storm or the space storms that occur?
Okay, so sun is the main source for
Mhm.
everything happening in that
Yes.
weather. So first thing we do is we observe sun. Now, one thing is it's not always effective to observe sun sitting on the ground. So we put satellites. We mostly put satellites in what we call is Lagrange one point or L1 point. So if you consider a reduced three body where there is a sun, there is a earth, and because of the presence of the gravity of these two bodies, there's a particular region in space we call the Lagrange L1 point where you can put the satellites for a nearly stable orbit. So we put our satellites there. We also put satellites close to Earth. Recently, we have sent a few satellites there, and we try to observe the behavior of the sun and in different wavelength, be it like just taking photo of the sun in normal wavelength or infrared wavelength or other wavelengths, or maybe get the description of plasma, what kind of plasma is coming from sun to earth from various plasma experiments happening on the satellite, and we try to keep an eye on the sun always. That's the first thing. And now, then we get those data and try to use models, be it completely physics based or be it from statistical or analytical understanding of our all previous histories. And then we try to see, okay, sun is behaving like this, which means that we are going to have a storm in next 2 or 3 days. And now you understand here are the uncertainties are really high because we have very less observations because observation points are less and the statistical data is not always very helpful. Mostly it is helpful, but not always. So, because sometimes it may happen that your satellites probably missed the local plasma environment that ultimately reached Earth, or your satellite flagged that you are going to see a huge plasma coming to Earth, but then it got lost and avoided Earth. So there are scenarios like this. But so if I just streamline it in one line, we observe sun. We first look for the basic signatures that sun provides to make us understand that there is going to be adverse space weather for us in next 2 3 days. Then we try models to see that how much adverse is going to be, which are the sectors that we are going to see problems, and that overall scenario gives us a prediction towards space weather. It's still not as robust as we have that normal weather prediction. Like we can do a weather prediction for 7 days, or even for a month almost, with some uncertainties. We still don't have that much capability in terms of space weather prediction. But yep, I mean that's our goal.
This is so much new information which I wasn't familiar with before because I remember when we first talked, I was confused about like space weather and I wasn't like familiar with it, but you did a really good job like explaining it and like it
Thank
makes
you.
more sense now.
Okay, good.
So I
Um,
assume you guys use like programming languages. So like or
a
what type
lot.
yeah, so like what type
Uh,
of languages and tools do you guys use in your research?
So, with current development in Python, Python is our like day in day out tool. That's uh, like easy to use, very much versatile in terms of as a platform. So Python is obviously our number one language that we use mostly. And for me, I use Fortran. Fortran because what we do is when we simulate or create a computer simulation of the space environment of Earth, it's a huge space in 3 dimension. Think about few thousand kilometers in one way. So the length is huge, the volume is huge. So you cannot do all this on your laptop or a desktop you have. You need supercomputers. And all these supercomputers, you need high performing language like and Fortran or C++. I know a few people also use C, C++. So for me, it's Fortran and Python, but it's in general, it's C++, Fortran, and Python.
I see. And so like what does like a typical day for you look like as a researcher?
Okay. I don't want to give you much details about this. No, I want to be optimistic on this. So we started with the question that was the main challenge. It's uncertainty. So one thing is anxiety. That's a byproduct of uncertainty. So for a researcher life, anxiety is a part of life. So my day starts with anxiety, and but it's a happy anxiety because ultimately I'm anxious about something I love to do. I have a lot of expectations on the results, so that brings up this anxiety. So I'm not uh, questioning this anxiety, or I'm not like arguing that why I'm getting anxious, but that's a part of a researcher's life. But other than that, yep, coding, getting huge data, like terabytes of data from that simulations, analyzing those simulations, try to see, are we breaking some physics, or are we making like actual truthful science? Are we getting the results because of it's the coding, the way we have done the coding, or is it actually true in terms of physical sense? This is my almost everyday job. Sub Run, analyze, see if the physics fits in.
Do you enjoy it?
I love it. I just love it. Uh, I love it because it gives you a sense of achievement when you see that you have done something that's actually physically making sense. So it's not some magic or something like this. It feels like it's magic, but it's not. And that's a beautiful uh, experience to see. For example, I mean, I can give you a basic example. Let's say you are solving a huge differential calculus or integration. And at the end, you have like doing the calculation for 3, 4 pages. All those functions you have used, and at the end, you got a result that the correct results. And
Yes.
that satisfaction is unmatchable.
No, I get
So
what you mean.
it's that's what it is, but in terms of computation and data analysis and interpreting.
No, like the calculus part, like I get it. Like every time I solve questions and stuff, like it's so hard, but the end result makes me really happy, and I'm like, oh yeah, like I can do this now. No, that
Yes,
makes sense.
yes.
So how much would you say like your work is like coding based versus like physical research?
Uh, okay, it depends time to time, but I would say it's nearly 50-50 to 60-40, more
Mm.
weightage towards coding. So 50-50 or 60% coding, 40% physics. Because currently what I'm doing is I'm developing certain new tool. So that's why I'm doing more coding. But when this development is ready, we have done enough tests, we have done enough validation through observational results and all. Then you would go completely on the other way around. Then you would do more physics than coding.
That makes
I,
sense.
I, yeah.
So now talking about like some questions the audience may have, what advice would you give to high school students that are interested in astrophysics or like space science?
Hmm. Uh, so first thing is I'll tell them to be curious. Okay, it's the curiosity that brought the mankind from cave to where we are.
Yes.
Otherwise, we would have been my cave people. It's the
Hmm.
curiosity that brought us here. So don't don't ever be not curious. Be curious about everything. Learn things. Don't be afraid of learning, particularly math and physics. I know a few people when I tell people that I physics major, people think like I have done some alienish thing. It's not. It's describing our day-to-day life with logic is all science is. So whatever we see around us in nature, we would like to describe nature with some logic. That logic is math, and the description is basically mostly physics when you talk about physical things. And so don't be afraid of learning, and try to focus on building like strong fundamental ideas and keep ask questions. So students like should ask completely baseless questions. that they think is baseless but is not. For example, when I was in eighth standard, I asked my physics professor, my school teacher, that what if I put a frog in outer space? I mean, maybe a bizarre question if you think about now, but but now, but as a teacher, if you have to answer this question to a student, you have to explain him or her, the student, so many things. And now that will generate curiosity to the students. And this is like a cyclic process. So curiosity brings more curiosity, brings more learning, brings more curiosity, and that's all. So yeah, I think I am by giving so many examples, I don't want to make the answer complicated. But yeah, I hope I made sense to you.
No, that makes sense because like also for AstroLaunch, like at the ending, I literally say like stay curious because if I wasn't curious about aerospace, I wouldn't be here interviewing individuals because I was curious about like their jobs and how that would help me understand like
Ex-
aerospace as a person.
exactly.
Yes.
Another thing for the student, I must tell you now, is to develop skills, particularly computational skills.
Mm-hmm.
So nowadays, coding has become much easier. Like you can ask any AI model to code 5 lines for you. So it has came down to write a code to write a better prompt for AI model. So how better you can describe your problem to a AI model to they give you a code. But that's not a solution. I would rather, I mean, if any students is listening to this, I tell you that think AI tool as a calculator. Your mobile has a calculator app. So let's say you have to do a 5 digit by 5 digit calculation. The best thing you do is you put that values in calculator. It gives you a results quickly. Use AI tools like that when it's ultimately necessary. Use AI tools then, but you must also learn how to do multiplication and division
Mm-hmm.
so that you don't have access to mobile and but you have an access to pen and paper. You can do a 5 digit cross 5 digit multiplication by yourself, but just to save time you use the calculator on your mobile phone. And in that same analogy, use AI tools. They will be there to make your edges more sharper, but they shouldn't shape you. The primary shape should come from you. So learn all the tools. That's uh, uh, for example, basic Python, basic C, basic Java, even starting with basic Bash code. There is hash codes in where you use terminals in like that. So all these things people should, particularly students, should look into.
That's so true. Like me being part of the generation that really relies on I think it's really great advice to tell students to not depend on AI because I go to school, like I know my peers really depend on AI and people get flagged for AI because we're not developing those skills that the generations before us used to develop because we have so much leverage to using tools that we should not be relying on. So I feel like that's such a good advice, and high school students should really learn the skills first and only use AI to save time or to help them with complicated issues.
Exactly. So, see, from a more philosophical understanding, every technology that is that has sustained in the whole world was there to save our time and effort,
Yeah.
make our life effortless. AI is also there to make our life effortless. If you think positively about AI now, but that should not stop us from learning. So
Mhm.
a car always make our life effortless. We can go anywhere easily, quickly, but
Mhm.
that should not stop us from walking, right?
Yes.
That's the whole logic of AI. Use AI because that's a great tool that saves your time, that can maybe improve your coding skills, that can maybe improve how you look the algorithm and logic, how you can. better yourself. Use AI as a tool to make your skills better, not to replace your skill with AI.
That makes sense. Now,
Yeah.
lastly, I wanted to address some future questions. So, what are some big questions that astrophysics and scientists are still trying to solve or answer?
In particularly my area of research, the primary and uh, big question, I'm sorry, is that how quickly we can do the prediction of adverse space weather and how long, I mean, let's say how many days in advance we can predict the space weather. That's the big question that we have, and I'm very hopeful that we're going to solve it in this decade. But that's one of the big things. From fundamental physics point of view, there's something called magnetic reconnection that's really important physics in the science that I do. We still don't fully understand magnetic reconnection. That's an open space of science if you want to do fundamental science in there. And then see the science, and again, the space weather is a multi-scale physics. By multi-scale, I mean sun is huge. Sun to Earth distance is huge. It's in million kilometer. But so when you look for physics, you look for a physics that remains more or less valid for a million kilometer. But when you come down to Earth, that million kilometer becomes a few meters. So then you look for physics that remains valid in these few meters. If I give you a quick example, let's say all the medium is plasma. So when you mathematically describe plasma for a long distance, for example, a distance from Sun to Earth, you say the plasma is like fluid. Fluid means like water, like gas, like air, but it has magnetic properties. So we use magnetohydrodynamics, magnetic and hydrodynamics. So magnetohydrodynamics to describe plasma when the length scale is huge. But when that length scale comes down to smaller length scales, we come down to kinetic description of plasma, where each particle, their movement, how they are influencing the movement of other particle, all this comes important. So understanding this length scale in this huge volume of space and then coupling those length scale, these are the challenges that still we need to make ourselves like better.
And then, do you think that space exploration will increase the career opportunities like in the future?
Oh, definitely. Definitely. Uh, the more we will be improving our infrastructure, the more we'll rely on space-based infrastructure, more satellites. More satellites mean more housekeeping on the satellites so that they don't deorbit, and more engineers and people involving in this understanding. So it's always gonna need some people sitting in an office looking at a satellite so that it and make sure that it's working for us. So definitely.
This was such an interesting conversation, and I learned so much about astrophysics and space weather and what it's like doing research in this field, which I was definitely curious about. And hearing about your journey and your work with space and Earth interactions and modeling was really inspiring, and I hope our audience
Thank
also
you.
had a great time. I really
Thank
appreciated
you.
taking your time and coming on this podcast and sharing your experience and advice. And I know our listeners will learn a lot from this conversation as well. So thank you so much for being on this podcast.
No, it's pleasure is mine. Thank you for having me here.
Thank you.
Thank you.
Thank you to everyone who joined me for today's episode. I hope you all learned something new and felt just as inspired as I did. Make sure to join me next time for another conversation that inspires curiosity and learning. Till then, explore, engineer, and elevate. See you next time.